Now let us prove the third part of the theorem. The third part states that all finite fields with q equal to p to the f elements are isomorphic to f sub q. Now let's prove this. Let K be a finite field with q equal to p to the f elements. And we make the following claim. We claim that there is a field embedding iota from K to omega. And as a consequence of this claim, and the uniqueness we have proved in part 2. Remember, in part 2, we have shown that there's a unique subfield of omega with q elements. Because iota of k, because it's the field embedding, has the same cardinality with k, which is q equal to p to the f, which is same as the cardinality of fq. By the uniqueness, we must have k isomorphic to iota of k, which is fq. To verify the claim, we shall use the following general lemma. The lemma states that let K over K be an algebraic field extension, and phi from K to C be a ring homomorphism, where C is an algebraically closed field. Then there exists a ring homomorphism sigma from K to C, which extends phi. Before I move on, I have to state that this lemma is due to the math stack exchange user Krish. Now let me first show you how this lemma implies the claim. To use the lemma, we take little k to be the finite field z mod pz, which is by our notation f sub k. And you think of this as a subfield of omega. And we take the capital K in this lemma to be a copy of fq in omega, where q is p to the f, which is naturally an extension of fp. From here we see that k over little k is an algebraic field extension, because we have shown in part 2 that any x in k is a root of sq minus x. This was shown in the part 2 of the theorem. And this is a polynomial with coefficients in fp. So this extension is algebraic. And now we take this phi in the lemma be the natural embedding of fp in omega, sending just 1 to 1, and extend this naturally. It follows from this lemma that this phi can be extended to a sigma from fq to omega. And now we claim that sigma must be injective, a monomorphism. This is because any non-zero ring homomorphism between two fields must be injective. And that follows from the fact that fields have only trivial ideals. Indeed, you look at the kernel of sigma, and this is a an ideal in FQ. So either kernel is equal to 0 or the whole field FQ, because FQ has no non-trivial ideals. The latter case is impossible because sigma is a field extension of phi, and phi is non-zero. So sigma must be also non-zero. So the kernel cannot be the whole field. So the kernel must be equal to 0. And therefore sigma must be injective and a monomorphism. Because sigma is monomorphism, it must be an embedding of the field FQ into omega. And this verifies the claim here. Now it remains for us to prove this important lemma, and we are done. To prove this, let script f be the set of pairs f, little f, where this capital F is an intermediate field between little k and big K. And this little f is a ring home from F to C, satisfying that the restriction of little f to little k is equal to phi. Namely, this little f is some extension of the ring home. We observe that this script f is now empty, since it contains at least k, phi itself. So this is now empty. And now we define a relation on script f as follows. We say f, f is less than or equal to f prime if this capital F is contained in capital F prime, and the restriction of f prime to f without prime is f. It follows that this relation is a partial order, and together with this relation, this partial order, script f is a partially ordered set, poset. This means partially ordered set. And now, as some of you can imagine, we're going to use Zone's lemma. To use Zone's lemma, we need to verify that every chain in this partially ordered set has an upper bound. Why is this so? We pick a chain, f sub alpha, little f sub alpha, indexed by alpha. And an upper bound of this chain can be taken as the union of those fields in this chain together with the map, which is denoted by f sub the union, where this f sub union is defined by its restriction to one component f sub alpha just equal to f sub alpha. And you can easily verify that this union is a field, and this guy is a ring homomorphism from this field to C, because this is a partially ordered set. For example, if you take two elements, one in f sub alpha, another one in f sub beta, and alpha is less than or equal to beta, then the sum of those two elements must belong to the bigger one. And this should be very obvious to you to verify this is again a field. And this guy is a ring homomorphism from this field to C. Now, because every chain has an upper bound, by Zone's lemma, we have that this partially ordered set has a maximum element, which we denote by capital F, comma sigma. And now we claim that F is precisely equal to K, the desired K in this lemma, and sigma is that ring homomorphism from K to C. And we are going to verify this claim by contradiction. Indeed, if not, then there exists an x0 in K such that this x0 does not belong to F, because by our construction, we already know that F is always contained in K. So what happens if they are not equal? If they are not equal, then there exists an element in K that does not belong to F. So there is an element in K that does not belong to F. Now, let Gx, a polynomial with coefficient in F, be the minimal polynomial of x0 over F. This minimal polynomial exists because this extension K over K is algebraic. And we know that this g of x can be actually taken in K join x. And now by field theory in abstract algebra, we know if we adjoin the field F by one element, this x0, then it is isomorphic to F adjoin x mod the ideal generated by g of x. This is a field homomorphism. You can verify this by sending a polynomial here to its evaluation at x0 and verify the kernel of this guy is precisely the ideal generated by g of x, because g of x is the minimal polynomial of x0. If f of x0 is equal to 0, then by the property of minimal polynomial, g must divide f. So f must fall into the ideal. This should be a standard fact in abstract algebra field theory. Now for any polynomial p of x in the polynomial ring over F, let p superscript sigma of x be the polynomial in the polynomial ring over the field C. Remember, C is our target field, which is an algebraic closed field, obtained by applying sigma to the coefficients of p of x. Recall that this sigma is the ring homomorphism from F to C. So the F comma sigma is a maximum element in this partially ordered set. Now, since C is algebraically closed, G superscript sigma of x must have a root in C, say alpha. And now we define the map psi from the polynomial ring over F to C by sending any polynomial here to p superscript sigma of alpha. Now by our construction, psi of g of x, which is g sigma of alpha, is equal to 0, because alpha is the root of g sigma of x. So g of x must be in the kernel of psi. This means psi induces a map, a ring home, psi bar from the polynomial ring over F mod the ideal generated by g of x to C. Now, using the identification that F adjoining x0 is isomorphic to the polynomial ring over F mod the ideal generated by g of x, we see that the pair F adjoining x0, comma, psi bar is an element in script F. Because psi bar is a ring homomorphism from this guy to C, and this guy is identified with F adjoining x0. And furthermore, if you restrict this psi bar to the field F, you will precisely get the map sigma from F to C. And that sigma from F to C, because F, sigma is an element in script F, the restriction of that sigma to little k by the construction of script F will be precisely phi. So this is by the construction. And therefore, this pair is indeed in F. But now we have a contradiction. The contradiction is that this F, sigma is strictly less than F adjoining x0, psi bar, because this field is strictly bigger than F, and the restriction of psi bar to F is sigma, because x0 is taken outside of F. So this guy is strictly bigger than F. So in this partial order, F, sigma is strictly less than this pair. And this is a contradiction to the maximality of F, sigma. And this contradiction comes from our assumption that F is not equal to K, so that there exists such an element x0 that belongs to K but not in F. So as a consequence, F must be equal to K. So this claim is true. And this finishes the proof of this lemma. We have found an extension of the map phi from K to C to sigma K, which is now equal to F, to C. So this finishes the proof of the lemma, and therefore finishes the proof of the third part of our theorem. So we are done.